see you'd be live, I think, and just have to do a little crap here to be able to see the chat. So I have to go through this little bit of a process, blah blah blah, and such. And still has the wrong icon, but whatever. I'll worry about that some other day. Yeah, icon, but whatever. Click on it. I'll worry about it. Okay. And pop out the chat and there. Okay. Should be getting better at this. Should be. Anyway, all right. So I figured to do an overview. I've been listening to an audio book, which on physics that was written, I think, in the early 1900s. So they knew about electrons and protons, and I think neutrons. But it was before quantum mechanics, but all the real wooey stuff. But there was, still this perception that ether is the only explanation or something like that. So it sort of highlighted the Maxwellian kind of view and the Young view, and didn't pay much attention, I guess I would argue, to the fact that the photoelectric effect and these other things kind of demonstrate that it's not it's less than nail in the coffin evidence kind of a thing, and that the similarities, any similarities between, you have to be very careful because something looks like that it is like. And so anyway, what I observed is that much of the book was a description of all these individual players and their individual contribution to, finding all these little different facts about how something behaves. And then the minor bit is just who gets to decide what the conclusions are that you draw based on all of those facts that you collect. And I'd argue that the conclusions don't have anything to do with the underlying observations. So I'd say like Descartes was a etherist. All right, he didn't believe there was anything such as empty space, and so the big contrast between Descartes and Newton was basically saying there's a bunch of empty space and there's little bits, of stuff. So there's stuff, and then there's places where there's no stuff. And the stuff comes in these kind of two forms, this stuff called force and the stuff called matter. And they are interacting. Now, I don't think Newton went as far as to say the force sticks to the matter and is carried by the matter. But it's still, that's sort of an open question, exactly how Newton understood those reactions. But Newton wasn't a conclusion drawer. He was a observer, and he documented what he observed, and he didn't draw too many conclusions about what it is beyond pointing out that in certain cases you can make these arguments that it can't be a wave because it's doing a certain thing that only a corpuscle could do. So he did go that far as to separate himself from Huygens and Descartes, who were etherists. All right, well, anyway, so the long story is short is that, I think there are these identifiable elements that are so, I could argue that all the forces we know now move the speed of light. So the simple argument is that there's good reason to believe they're all the same thing, because it would be kind of coincidental, that they would have the same speed built into them and somehow be different things. That just doesn't make much sense. So I will start with just an outline of what I'm going to argue the evidence points to, okay, and just say that I can cite lots of different pieces of evidence that point to it. So I could argue against kinetic energy and just point to all the experiments where kinetic energy fails dismally. And, just that's all you need to do. Now, I'd like to be able to point out all the ones where it's success, where there's some success for momentum. But the fact is, physics never did any of those experiments. Again, it hasn't done the simplest experiments. It hasn't crashed cars, hasn't, turned scale sideways, hasn't done, a multitude, hasn't dropped 4 pounds 1 foot and 1 pound 4 feet. Hasn't done any of these experiments. And that's a big failure of the science, is that it hasn't been curious about these elemental, fundamental axioms and statements. It's made as conclusions rather than as observations. So they're not observations, they're conclusions. Now I'm going to state a conclusion, okay, that I think it's clear that all the energy comes from the force, and the matter merely absorbs that force in a form. It absorbs differentials in that force, and that's that absorption is essentially a condensation of force. It increases the density. So I have used the argument that you could think of the force as little Sisyphuses, and that they have two conditions they can be in. They can be flying free in space, and then they're going the speed of light. So that's a bit of force, a little tiny bit, okay. And or it can be pushing a matter boulder, that is an electron or a proton. So there's only two kinds of matter, and there's going to be two kinds of force, okay. There'll be an electron Sisyphus and a proton Sisyphus, but I don't need to get into that yet. And the two conditions that the Sisyphus can be in is if they're pushing boulders, and there can be more than one pushing in the same direction, they're going much slower than the speed of light. Okay, so when they're pushing a boulder, they've slowed down. Now, I can just say less than the speed of light, but it's substantially less, depending on how much force has been collected. So the more Sisyphus is pushing the boulder, the faster the boulder goes. And the maximum speed is obviously created by the fact that the Sisyphus only go the speed of light, so they can only push a boulder at its fastest, the speed of light. They couldn't push it any faster than they're going. And that simple analogy does work. So I'm saying the future will confirm, okay, that this, you won't find a piece of evidence that says this can't be true. Okay, that what I'm describing doesn't actually happen. All right, so the added bit, I might as well throw the added bit in now. Maybe we can go red and brown, maybe that'll work, I don't know. Black's getting kind of feeble. We'll put it over the feeble pile. All right, so there's the two kinds, and the simple rules are, if an electron, we'll just use this as an electron, gets hit with electron force and it's not moving, then it sticks and it pushes. The Sisyphus can push. Now, if it's already got a force bit going this way, so it's already got a Sisyphus going this way, and now a Sisyphus is going to try to hit it this way, all right, the reaction is sort of what you would expect from like a Newton's cradle. This Sisyphus will go this way, taking this energy, and they'll basically just exchange each other's motivation, and that this one will leave going this way. So this will stop moving, and you'll have a reflection in both directions, essentially. You'll have a transmission in both directions, however you want to look at it. You'll stop storing the energy pushing the boulder, and both objects will leave at the speed of light, of course. They're always, a free Sisyphus always moves the speed of light. So that's why you can't make a flashlight. You can't move a flashlight forward and make the light go faster than the speed of light, because it can only reflect off a surface and go the speed of light. It can't go any faster than that. So no matter how fast the object's going, it always leaves at the speed of light. But anyway, so I think that covers the interaction. So if this was 2 bits of force, let's say this came in with 2, then it would just reflect 1. Okay, and this reflects 1, and it would still maintain its momentum in this direction, its motion in that direction. And the key that makes the whole thing, that creates what nobody has described, which is how does charge function, is that if an electron force hits a proton, or vice versa, a proton force hits an electron, the reaction will be quite different. So if an electron force hits a proton, it just goes through and comes out an electron force. All right, so with that simple interaction, so you have You have the action of absorption, that is, it sticks. So absorption is sticking. You have the reaction of reflection, okay, where if something already has momentum opposing you, you're going to end up reflecting off of it. And you have this third interaction, which is this conversion. And with that interaction, that creates all of the things that we see in charges, where electrons repel electrons. So if I have two electrons, and you can understand that all of the red Sisyphuses that would come from this side and all the reds from this side would all be converted into brown Sisyphuses in here, okay, that would end up pushing out. And so you'd end up with a force, a constant pressure between the two electrons being generated by that conversion of the red force into the electron force inside. So inside is being created this pressure that's going to push them apart. Now the protons are doing the same thing in reverse. And then if a proton and an electron are associated with each other, then you have the bizarre effect where a proton force can't get to that proton. As it goes through, it turns into an electron force, then the electron force comes back out of proton force. So a proton force just goes straight through when they're paired. And there's no pressure inside. So no electron force can get to this surface, and no proton force can get to this surface. And so therefore there's no pressure between them. Okay, and they end up pushed right into each other because all of the red force coming from the universe pushes on the proton, all of the electron force pushes this way, and so they're pushed into each other. So it perfectly duplicates the function of charge with just an incredibly simple mechanism. So all I've done is created two kinds of force and two kinds of matter, and I've made charge, and I've made eventually dipoles, obviously. Electrons and protons would have a real incentive to stick to each other and create geometry eventually, where you can understand that this proton can't see this proton because of the electron's existence between them. And if I was to kick that electron out, you could understand that the two protons now would be doing all that conversion into a brown force between them, and there'd be a tremendous pressure. So it really explains the nuclear functions and what we see as a consequence in the real world. All right, so that's the detail. So it's a little bit, okay, I'm asking you to understand that this is a simple mechanism, and it creates what charge does, which is both attraction and then repulsion of the likes. So the likes repel each other, and the unlikes attract each other. So it duplicates it with a very simple mechanism. So I'm just saying it's certainly a good Occam's razor statement that you don't have to believe the simple explanation is the right one, but there's a high value, okay, in recognizing that the simpler the explanation, the better. Yeah, generally speaking. Because it's a simple universe. I mean, it evolves out of something simpler than the external thing. The battleship with its complex stuff is made out of the simple stuff of iron and aluminum, and so it's not more complicated than the thing it's making, and that's the tendency in the evolution of matter in the universe. All right, so. So once I've established that, I can now talk about the different mechanics of the free Sisyphuses versus what happens in space when matter is in this matrix of force. So we're just saying that there's a bunch of force in the universe, okay? And these little bits of force are all a vector. They're all moving in some direction at the speed of light, and there's no swerving in that duty. So all the forces have that appearance. Light, everything looks like, when it hits a surface anyway, that it must have been a ray. I mean, it certainly lands on the surface as if it's a ray of something. It doesn't land on the surface as if it's a spreading wave. So that's an absolute truth, pretty much demonstrated by even the experiments they think prove wave, they have to concede that the wave is isolated in space, that it doesn't spread throughout all of space, and things land in one location, as they state. So they have to create a duality. I'm saying there's no duality. You don't have to. You can just ignore the wave part, because the wave part really is just a frequency. So anyway, so the argument to be made is there's a density of this stuff. There's an amount of space between these little bits. And what matter does, okay, is it absorbs that energy. So you can understand that there's a distance between all of these bits of force, but when I'm pushing an electron, I could be consolidating a whole bunch of force in a very small density. So if I can get an electron to move, what it's done is taken force that's very spread, and it's increased its density dramatically, okay, by absorbing Sisyphuses. So the space per Sisyphus is reduced. It's a higher density. So in a sense, it's collecting force. And so you could argue that if matter is banging into each other and jittering about, moving, it means it's collecting this force to do that. So motion this way and motion that way, we think of it, okay, as getting somewhere. But you don't have to get somewhere to be using force and to be moving. And the moving part is the fact that little bits are stuck to it and the density has been increased. So the idea basically is that what's happening in the universe is things like the Earth, for example, end up collecting force because of their matter. So the energy, the force coming in from the universe essentially gets slowed down, okay, occupied, creating motion, and that motion is really a higher density. So it's basically absorbed, okay, some of this arrow, and the arrow coming out, okay, ends up being a little shorter than the arrow that went in by this differential. So it's not like it preheats an object. It's the heat comes in, the energy comes in, the pressure comes in from the external universe. These little bits of force are all hitting the object. So you can understand that if I did have a field of energy shooting in all directions, that a bunch of it would end up doing exactly what a light bulb does in terms of shooting rays out. They'd be all coming in, converging. I would feel like the whole universe was out to get me, because everything would look like it's coming right for me. But obviously that's only the stuff that I see because it hits me. There's a whole bunch of force that doesn't hit me. Okay, but it's going to feel like, or be like, I'm being bombarded from all points in the universe. And the simple truth is more force goes in than will come out, okay, now. So if you could think of yourself sitting here on the Earth, I don't know why I'm choosing upside down, but, you know, just trying to be fair. You can understand that the force from the universe is hitting you now, okay? It's a force coming at you. And the force that has to go through the Earth, that is, it's creating this higher density, okay, is essentially slowing down. So it's not going to get here now. Now, if I let this sit for a while with no force coming in, it would just radiate all that extra pressure out. But the fact is the extra pressure is in here, and the extra pressure is density. So I think everybody would agree that, you know, if I compressed this universe, I would increase the density, okay, and create heat. I'd make it hotter and hotter. Stuff would move faster and faster inside that box. And that's essentially what the Earth is a storage device. It's going to store the pressure, and it's going to store extra density by moving matter, by slowing it down. So the force doesn't go straight through. It goes through by pushing matter, getting slowed down. So it just isn't going to get to the surface in time to stop this object, or to the object in time to stop the object. And the simple truth is this object will just fall in that differential. And the differential has to be constantly fueled. So you can understand the Earth is hot in the center, very hot, 4,000 degrees plus, maybe 5,000. So it's a tremendous amount of heat. And you have to understand you can't keep making heat without fuel. And so what's the fuel that keeps the Earth hot? And the fuel is this constant process of more pressure pressure coming in from the outside, and it basically keeps pushing the stuff together that would fly apart. So it just keeps compressing, okay, which is essentially storing the heat. But obviously, as some of the heat, as the some of it finally gets through, okay, it's at an equilibrium over time, but not at this one moment. So at every moment, more goes in than comes out, and that's the simple differential that you fall in gravity. So gravity just means that there's more force hitting you from above than obviously gets through the earth and hits you from below at this one moment. Like I said, if I turn the force off that's coming down, then I'll go the other way, because the earth will radiate that force that it's stored as a higher density. Okay, and it will return to a true equilibrium with the universe. It'll give back what it stored. That's the simple argument. But it would do it, frankly, it would do it explosively because of the amount of pressure the Earth has stored. So you have to ignore that part and somehow keep the Earth from exploding and just let it radiate the heat. But the radiation of the heat is really what it's collecting every millisecond. It keeps refueling that furnace. Can't stay hot, can't stay 4,000 degrees unless it's being fueled. And the fuel is the external pressure, the external force going into the earth and condensing. That is being collected and forced into a tighter, you could just argue a frequency argument. The force comes in at that frequency, and while it's inside the earth, it's at this kind of frequency, this kind of density. And it's that differential, that storage of that one bit in the same amount of space, that means there's a bit short coming out. That might be a simpler way of understanding it. You can understand if I'm concentrating the number of bits, if I'm collecting them, that yes, less has to come out this one moment of time. All right. Yeah, that's not terrible. Yeah, that covers an awful lot, right? So the conclusion is based on all of that experimental evidence. So now if I was writing the book, right, I'd have to go through each one of these observations made by these different people about the function. Now, the key point would be is that physics doesn't explain charge. It just says it happens. And clearly, it says things about the heat inside the Earth that are just nonsensical. I mean, their explanation is on its face. You could recognize that can't be the cause. So they say the Earth is molten because of impacts, meteor impacts a billion years ago. And somehow the Earth is some great insulator and it doesn't let that heat out. Okay, so that's their explanation, that there's some layer in the Earth that's somehow some kind of perfect insulator, and the heat can never get back out again. Now, that certainly ain't going to work for explaining the sun. Now, so the sun, they come up with fusion as the explanation, which is also doubtable in terms of recognizing that that's more energy in than energy out, frankly. All you can get back is what you put in. If you're going to use pressure as a system to create energy, you can only store it. And the fact is that pressure stores energy. So, again, it's gravity that has to be the cause of the effect. So anyway, and the other explanation they use is radioactivity inside the core of the Earth. But obviously all the radioactive elements that we know of have a half-life that's much shorter, than billions of years. And there's no way you could, obviously you can't get anything out of something, that had an infinite half-life. It's never going to decay. So you need it to decay to get energy out of it. And so, there's just no way that the Earth is making uranium. So you'd have to argue that the temperature would slowly go lower and lower and lower, because half your fuel every 10,000 years, half your fuel is gone. And the fact that you're concentrating it to create the heat means that the half-life goes down to even 5,000 or 50 years even, you're going to run out of fuel really, really fast. So that can't be a possible, reasonable explanation that the Earth is burning uranium. And look, it's just so obvious that gravity produces pressure. So I shouldn't even have to, I shouldn't even have to make the argument, because everybody, I think, would agree that if I put mass on the Earth, it applies a force to the Earth, a weight. Like something like 75 joules of energy for a 150-pound person is being pushed into the Earth every second. It's a lot of energy. Your mass, your weight, and that the weight adds. So the weight here and the weight here and the mass here, it's not falling with the same pressure. I mean, it's not. It gets lighter and lighter as it gets deeper and deeper. But the fact is, it's still all weight. So it's this giant column of weight this way and another giant column of weight on this side. And obviously the pressures get insane towards the center of the Earth. And obviously high pressure, you have very good reason to believe that applying pressure creates heat. Like there's no circumstance, I don't think, that could be described where applying pressure doesn't require the expression of some heat loss. Now, once you have applied a pressure, then you're not going to create any more heat once you have stopped applying more and more pressure. But the application of pressure will create heat. And that's what the Earth is doing constantly, is applying pressure. So you can understand why it's hot. By just a pressure argument alone, that it would make perfectly good sense that if all the mass is pushing and it's getting higher and higher pressure as you go deeper and deeper, you'd have to say it has to get hotter and hotter as it gets deeper and deeper, by just logic rules. There's the catch that in the center there's so much pressure that the matter in the center of the Earth can't move anymore. It's a solid, and it's stuck being a solid. And so the simple argument would be is that the more solid it is, the more it transmits the force without delay. So the more perfect your conductor, the faster the electricity will get through it, theoretically. So that in some sense makes perfect sense. So that's, I don't want to spend the whole show defending gravity and making the simple argument that it's just kind of obvious that it is a push averse, that it's pushing because the inside is under pressure. So I'm just saying they keep calling it a pull, but clearly the pressure is being created by an external force pushing in, not some internal vacuum that somehow is pulling. And again, it would have to be logically a vacuum to pull by our own understanding of how everything works. So I could talk about when they put the two half spheres together and suck the air out, and what holds the two spheres together. Well, it's not something on the inside. It's the air pressure on the outside, and it just demonstrates how strong that air pressure is. I could use the newspaper on a flat surface and explain how, you could put a stick under the newspaper and you can break the stick, so you can apply a lot of force and it doesn't rip the newspaper, because the weight of the atmosphere on top of that paper is this meter of air, and it has this incredible weight that it's applying to the piece of paper. So there's lots of experiments that demonstrate this pressure effect, and that it's always from the outside. There's just no reason to believe that there's some, internal mechanism. Like I said, the vacuum isn't a pulling mechanism. It's the high pressure going to the low pressure. It isn't as if the low pressure sucks the high pressure. No, it's the high pressure aggressively pushes into the low pressure. So I can just incrementally change the pressure, and the external pressure is always the force pushing into the lower pressure. The high density pushes to the low density, It's not the other way around, that the low density pulls on anything. And again, that just has to do with understanding the fact that it's a momentum universe, it's a motion universe. Motion's everything. So the force, the Sisyphus, has motion, and it gives it to the carrier of the boulder, and the boulder can release that force and release the pressure of whatever Sisyphus is it's collected in its motion. All right, so I think that's it's. So I'm just saying, so you could make all these arguments, and again, it's going to come down to this bottom line of what do they have evidence for. And so let's go through the arguments for, all right, so even the gravity argument I can turn into sort of an argument about what we know about electrons and protons. So we'll go to the atom. So the idea is once I make these electrons and protons, that's not a very good color difference. What color is that? It's supposed to be red. Yeah, I guess the brown is now red. Supposedly. Yeah, I think so. This must have been brown. Okay. That's getting kind of weak too. Alright. Gotta find some more markers, I guess. Alright, so I have an electron and proton. I get them to stick together. Now, obviously, what physics has learned is that, the neutron, decays into an electron and a proton. I don't know why I put it in there. Yeah, that was that. All right, so they call this a neutron, or they call it a hydrogen atom, but that's the simple relationship. And the argument is that you can take this simple configuration and you can just keep building on it. And so the argument would be, again, is I could put another electron over here, and then I could space electrons over here, okay, and over here, and I could build an object out of this. Now, the key is that it's, the nucleuses always have the protons in them, and the electrons are on the outside. So let me do that. Should have done that first. So I did it, essentially backwards here. All right. So the physics has this diagram, this definition. They compared it to solar systems. They did lots of comparisons. And again, I think, it's just obvious they drew conclusions that just don't make much sense. And one of the key ones was where they said, well, we know how atoms stick to each other. It's by sharing an electron. And then they had this idea that somehow that shared electron is orbiting both nucleuses, which just is too ridiculous. And right there, they should have said, okay, that theory doesn't work anymore. Because if we're going to use the idea of a shared electron, it really can't be on opposite sides of that mechanism and still hold it together. So obviously, I'm arguing for a kind of magnetic model. So the idea is the protons are much heavier, okay, than the electrons. So it takes more force to move a proton, okay, than it takes to move an electron. 1,000 times more force, you could argue. So that's the reason why they get stuck in nucleuses. And so what you really have in nucleuses is electrons binding protons. All right, and so you end up with this 2-to-1 relationship between the number, okay, of protons and electrons. And depending on how you configure this object, I could put a proton over here and a proton over here. I could have a proton on this side and a proton on that opposite side. But there's lots of ways I can configure this object, okay, to maintain this 2-to-1 relationship. And the helium nucleus essentially does that. And so you end up with 2 more protons, okay, and you end up with 2 electrons. So if I just move this electron out this way, okay, don't have it perfectly centered, you could understand that I could have, an arrangement of 4 protons. Let me see how I can draw that. Maybe this way. Proton, proton, proton forward, and then proton back. So one of them's behind the other one. And then you could argue you could have the 2 electrons on this side and one on that side. And the simple argument is that they're attracted, the electrons are attracted to all the protons from both sides, but they're repelling each other. The electrons can see each other, and so they're repelling each other, and so there's a balance, a tension. And so, you know, this object would be your helium nucleus, and then you would just add another one of these neutron plus a proton objects and just keep building on that nucleus. So the nucleus isn't all positive. It's only net positive because it has twice the number of electrons as protons. I guess the simple argument is the neutron should have never been declared a particle, because the neutron really is just a proton and an electron really close to each other. When they're further apart, they're a hydrogen atom. So when you bring an electron and proton close, neutron. Pull them apart, they're a hydrogen atom. And again, to some extent, physics concedes this. So it's, you know, it's not a statement for which they have any, their stated philosophy is still consistent with that argument being true, that neutrons basically decay into hydrogen. They say an anti-neutrino flies out also, but it's a little bit too ridiculous to waste time on that kind of nonsense. All right, so the idea is that you have this composite object as a nucleus, and from some positions, okay, I'll just do this. It's going to look negative. So if I looked at it from here, it would look like it would look negative. If I look at it from here, it's going to look very positive because I can't see either one of the electrons. If I look at it from here, it's also going to be positive, but I can still see the electrons, so it's still going to be purplish. So you're really just saying, where do I see purple, where do I see blue, where do I see red? And that will describe where the orbiting electrons would be. So the electrons want to avoid the other electrons, so they're always going to find a location where they can see the most proton and see the fewest electrons. So they're going to have, no, wrong color. They're going to have positions, okay, where they can do that on the exterior of the atom. So I didn't do this proportional to the real distances. The nucleus is small and the electrons are kind of far away. But I would argue, you know, that we don't know exactly how big these things are in proportion to each other, but the argument is that they all have the same charge. So the strength of the positive force is the same as this negative force of the electrons. So you could argue they have to have the same spatial dimensions. They have to be the same size, and as stated, it just happens that the protons are heavier. But anyway, so from that diagram, you could understand that the nucleus is net positive, has more protons than electrons, but it's polarized. So it's always got places that still look like a north pole and places that look like a south pole, technically. And the electrons will arrange themselves consistent with that. But so what you're ending up with is, so you got this net positive, and then you have these negatives on the outside. So what are the two atoms? Say if there's another atom over here, what is it really going to see is that these, always color problems, the electrons are going to see each other, okay, more than they're going to see the net positive nucleus. It's very small, and the electrons are on the outside. So you can sort of understand that atoms are innately don't like each other much, okay, in the sense that they're always seeing the other atoms as a net negative, because the electrons are closer to them than the protons. So the protons are always further away, you know, in terms of their vision. The protons are always further away than the electron. So the electron looks big and the proton looks small. And so that's why atoms, especially in gases, seem to have an infinite capacity to say, I don't want to be next to another molecule of this stuff. And the key is the only way they can be next to each other is they have to hit each other with enough energy where one of these electrons is disposed of, and now they share an electron. So it's only when they, I'll draw that with some other color. So they need to get rid of one electron So there's a point where they'll share one, okay, and then you can have another nucleus over here, okay, that positive, and they're literally sharing this electron as a bound object, you know, having attraction and repulsion that's in balance. And so these are all balanced positions based on where the positives and negatives in the nucleus are. And so the next electron, you could argue, would be out here somewhere, right? I mean, if you're going to put another electron in this system, you'd say, oh, it has to be here because it's repelled by this one and repelled by that one, and then it's still attracted to the net positive nucleus. And so you're just building geometry. And that's why there's only 100 elements, is because, well, there's only so many geometric shapes you can make, okay, that are going to hold together, that you're going to be able to maintain a pressure balance between these constituent parts. So, now when you push atoms into each other, and they don't combine, that is, they don't share an electron, clearly you just end up creating this pressure in the electrons. So the electrons would start pushing into each other. I got to erase here. So you can just sort of understand that all the electrons can see the other electrons. It's all line of sight, you know, except the ones that are behind a proton, of course. You know, but they have a line of sight, and they're seeing, you know, these colors, you could argue, and it's really just about seeing a balance between the positive and the negative. And if there's no balance, then they can get closer and closer until there is a balance, and that's all it's striving for. So I guess I should make that point just to clarify. So if I had objects, you could sort of understand that I could create this with magnets, you know, where I have a South Pole magnet and then I have 4 North Pole magnets, and I could put them underneath a piece of glass. And there's an arrangement where I can set them in positions where the force each one is feeling of attraction is compensated by the repulsive force between the likes. So the likes are repelling each other, okay, and they're attracted to the center. So you can sort of understand, this one can't really move in without pushing on these two, increasing the pressure. So it's kind of, they're all stuck in a pressure equilibrium. And the pressure here is going to be the same as the pressure here. It's going to be the same as the pressure here. So all the electrons are sharing that pressure. And you could just understand that it would be a condition that could be elastic, in the sense I could push a little bit this way, and this would push back, and this would just, and it would compensate, and it would jitter, and then it would go back to this equilibrium of the pressure. And so this is sort of the idea of why atoms can absorb energy or store energy, is that I can change that pressure. That is, I could apply a force and maintain it. That is, I could have a bunch of other atoms and they're all pushing on each other, and the whole thing just keeps pushing, and so these electrons get pushed closer together, and these and they just get, I'm drawing them as protons, sorry, but just a mistake of my drawing. They push into tighter and tighter relationship to each other. They get closer and closer, and the closer they are, that means the more capacity they have to repel, because they're, again, remember, they're converting all that blue force into red force between them. Again, I'm sorry about the color change. And so the pressure increases the closer the electrons are to each other. And so it makes perfectly good sense that, in substances, I can add charge by just adding an electron. I can put another electron, say I have a matrix of these electrons, okay, where, well, technically they're sharing an electron somewhere in here, but anyway, where they're in a relationship where the pressure is shared between the atoms, and basically I could just hit on one electron, it'll push on all the other electrons, it'll push on the electrons in the other atom, then they'll all dissipate the pressure throughout the whole system. So I can just keep adding electrons and increasing essentially the voltage, which is the mean pressure of the entire object, the substance of all the electrons. And so I can just keep adding pressure and adding pressure by adding electrons and forcing the electrons now to, they have to stay in the same space, and they have to, basically absorb that extra electron by increasing the decreasing the distance between them. And in that sense, store the energy as a storage of mass. And that's exactly what happens, is things gain mass when they gain electrons, obviously, and become charged. So that's all about electrons. So what about the proton force? So the proton force obviously doesn't have much effect on electrons, except in the fact that it's converted into the force pushing them apart. But there's no correlate. I can't push on an atom with the proton force, but I can push on atoms with the electron force. So that distinction needs to be, it has interest in the sense that we know there's a certain amount of energy in the universe, but we're measuring the energy by measuring only electron force. So the only thing we measure is the frequency of bits of Sisyphuses and their motion through the universe. So I could have a blue light versus, I drew them too much the same. Blue light versus red light. Blue light would look like that. Red light would look like that, and blue light would look like this. So it's just the frequency at which the Sisyphuses, how much density they're in. And obviously, you can just make the point that if all you were going to do is get hit by that density, and I had a starting point, you're going to understand that the closer ones together are going to have more energy in less space. So if I just went by the density of the force, you could understand that, yes, there's more force in a smaller space. It's not more energy, it's not more bits of energy, but they are in a higher density, which means they represent a higher pressure. And, so they can apply a higher pressure when they hit something, but the higher pressure isn't being created by more energy, it's just being applied by a condensation of the energy. There's more energy per inch or per moment of time. So if this hits you, you need a greater, longer period of time for this to hit you than this to hit you. And it's that time that makes things that are fast seem like they have more energy than things that are slow, because they're applying the bits at a quicker rate, more of them in a shorter period of time, which obviously is more disruptive to a system. So if I applied to that thing I called before, the deuteron, is what the physics calls this object, exactly the opposite again, the colors are reversed, and I knock this thing in the middle out, the force I'm creating, the pressure that would shoot it out, the strong force, which really doesn't exist. The strong force is an electron. You stick an electron between two protons, the protons will gladly get very, very close to each other. But if I knock that electron out, I have a tremendous amount of instant pressure created. And so there'll be a lot of momentum pushing them out. All right, so that's what consolidating the force can do, putting it under higher pressure, is it can create a lot of motion quickly. And so a quick motion is exactly what can knock that electron out. A lot of force applied quickly will knock it out very quickly, because there's no time for the other force to hold it together. So if I hit that electron quickly, I'll release it from its condition, because the compensating force, that is the force of attraction, takes time to happen. And the force of repulsion takes time to happen. If I knock it out quickly, the other forces binding it have no time to react, so they're weak. So this gets to another gravity argument that I've made over and over, but I'll make it one more time, that it's just about time, and how much time you're being exposed to a force. And so you can understand that the quicker you can move in any system bound by force, the less likely the force can have any elastic capacity to hold you. So the less energy you'll have to apply, the more energy you apply, as funny as that sounds. So the more energy you apply, the less energy you need to escape a circumstance. So the simple argument is if you had a gravitational body and you were just going to fly by, the faster you fly by, the less you get bent, That is, the less energy you have to use to counter the force of gravity. And the slower you go, the more energy you would have to use to counter the amount of force you're collecting. So it's a completely time-dependent force in the sense that it needs time to push you into the earth. And if you don't give it any time, you can't collect any. So if this was a paint sprayer, you could understand if I went through it theoretically as fast as the paint moves, I'd hardly hit any paint at all. I would get none on my surface, and I might get some on my front moving through. I might hit some paints that's still in space, but none of it could hit me if I'm moving faster than the paint is moving. So you could understand the simple argument that you gain huge efficiencies with speed. So the faster I can go through a force, the less the force can react, because it's always time dependent. It always needs time to apply, because it's moving at set speed. And so like little particles of paint, it needs time to be collected by any object going through it. And the less time, the less you collect. Simple enough argument. Yeah. All right. So this gets to, so again, it's just understanding that the forces we're familiar with are all the electron forces, because they're the ones that can move, that can create charge and create, well, they both can create motion, but the motions that we see associated with force. And I guess the catch is magnets will show you the proton force, but it's another understanding of that all you're doing is manipulating the force pushes on the matter. When the matter moves, it changes the force. So that's that famous thing where the matter tells the space where to go. Well, it's really the force, and then the force tells the matter where to go. So the two of them have to interact with each other, because neither can interact with themselves. Matter can't interact with matter, and force can't interact with force. And so they're a conduit to each other's reactions, you could argue. All right, so which one should I do? All right, so let me just say it again. So the electron force, so we have the right color this time, yeah, is in bits. And you can understand that a photon is just bits separated by a frequency. And the catch is that the bits also have a polarization. So if you had radio waves, there would just be this mile-long distance between one bit and another bit. And that's a consistent amount of it. So there would be, billions of little particles at this timed location, and then there'd be billions of little particles at this time location, and that would be a radio wave. And then as you get to the higher frequencies, you're just changing this distance and making it smaller and smaller and smaller. You're just making the frequency tighter and tighter and tighter. And between this amount of compression of the bits. Now, the obvious argument about how do the bits get compressed is every time an electron moves out, it's going to reflect everything. So when it's moving out, every bit that hits it reflects. It doesn't absorb any. They all reflect. And the fact is the energy keeps going this way because they keep reflecting off of this too. It keeps losing its momentum. So when it pushes out, it starts off really fast, goes really slow, and then stops. And then can do the opposite, go backwards. So every time an electron is oscillating elastically in the atom, okay, what is it doing? It's compressing, it's making the frequency, everything that hits ends up being closer and closer. So if I hit it with red light, I can essentially turn it into blue light. And then it does the reverse, going backwards. It's basically taking whatever's there and spreading it out, making it less dense. So it compresses and then expands, and compresses and expands, which is exactly this. Okay, that's exactly what this represents, is an expansion and a weakness in the density, and then a high density, and then a low density, and then a high density, and then a low density. So that's the frequency that is the electromagnetic spectrum. And so it's not really electromagnetic, it's just electro, in some sense, or it's all magnetic, however you want to look at it. But it's just a frequency. It's just the density of, the amount of space, okay, the force is in, and occupying, in this condensation of it, in the clumpiness. Let's just call it that even. And so that the other component the photon has is polarization, and that's created by the fact that when it hits a surface, it needs to hit the surface. Okay, it needs to hit the electrons in sequence. So there's the argument is that there's electrons built into the surface, and the idea is you're going to try to hit one, give it momentum. It's going to share the momentum with another electron, and then you want to hit that electron and cause it to have even more momentum, okay, which it will share with this one, and then finally you want to hit it again and add more momentum, and that'd be enough momentum to cause a cascade where the pressure just keeps moving between the electrons, and that's electricity. And then in the case of the ultraviolet, you're going to create the ionizing energy, which is you're going to hit these electrons hard enough, give them with their fast hits. They don't have any time to slow down. The atom doesn't have time to elastically react. So you're hitting the electron, it's going to get hit again, and then it's going to get hit again, and it's going to gain more and more speed. And really, again, you're not hitting just one electron. You're hitting an electron here, then you hit another one here, and then you hit another one here. So they're all different atoms. So the polarization of light is kind of huge, 500 or 600 atoms worth of polarization. So when it's hitting a surface, it's hitting a sequence of atoms. It's hitting the sequence of electrons that are in atoms, and it's hitting them as the pressure moves from one atom to another atom. It just keeps incrementally adding more pressure to the pressure you added with the first bit. So the first bit hits, it adds pressure. The second bit hits before that pressure stops and starts contracting. So it hits while it's still moving. So it adds to the pressure. And then the third bit hits and adds to the pressure. And that's electricity. That's how it moves in theory. Okay, and so that's all of the electromagnetic spectrum. And then the other phenomenon, magnetism, well, maybe I'll do electricity a little further before we go to magnetism. And I'm almost out of... I won't be able to draw anymore. Have to find something else to erase with, or use something else to draw with. Oh, that's no good. Yeah. Why? I don't know. I'm surprised. I didn't think I used that much. Okay. So I'll have to use the dry erase thing, I guess. Alright. So let's do the conductor electricity thing first. So it's really all just electron force, because you're just adding pressure to the electrons. So the protons aren't really playing a role in the photon effect. The photon is really just an electron event. And so that's what I'm basically trying to state. Alright, so you can look inside of a conductor. I guess we'll just draw it like this. And you can sort of understand that the atoms inside the conductor, okay, are in a condition. And what you're going to do is you're going to hit one of them with this extra electron, right? So I hit this one with an extra electron. What am I going to basically do to it? I'm basically adding pressure here, on this side. So I'm pushing the electron into the other, right? I have the positive center, and I have these electrons. And so what was the theory? If I push on this electron, I increase the pressure on these other two electrons, so they have to go out. And so that's why the magnetic effect, or the induction of the photoelectric effect, the induction of frequency, you could even argue. The fact is I put the energy in the wire, and I'm going to end up with an effect that comes out of the wire, a magnetic effect. And that magnetic effect is going to end up being transmitted as radio waves, or if it's high enough frequency, visible light. But what am I really doing? So I'm really just expanding. So I'm compressing the atom, and what I'm doing is just basically reshaping it. And now it's going to share that pressure with the next atom, so obviously it's going to be reshaping. The next atom will get a little more reshaped and all. So it'll degrade over time. But if I keep the flow of electrons coming, then I'm going to keep maintaining this oscillation in the atom, where it's just going to keep elastically expanding and contracting. And so, well, really just expand. So what I'm going to do is end up increasing the pressure inside the conductor, okay, the voltage. So I have a high voltage here, a high pressure of electrons, and that pressure is going to automatically move to the low pressure. So no matter what I connect to this that's conductive, the pressure will go into that thing and equalize the pressure. So the voltage, if the voltage is 100 volts here, the voltage moves through the wire, moves into anything that touches the wire that's conductive, and creates the same voltage, the same 100 volts at any one of those locations. I have the same pressure. So it just, like water, will do the same thing. I increase the pressure in one little tiny location, it increases the pressure within the whole fluid. So all the surfaces feel that pressure. So anyway, that's what I'm doing. And so obviously you can understand with oscillating or AC current, what I'm doing is constantly changing the atom. I'm forcing it to expand, contract, expand, contract, expand, contract. So it's just going back and forth with which way the pressure is being applied from. And so I'm just constantly creating at the frequency of that current, I'm constantly creating this change where I've pushed electrons out of the surface. So that's the key point I wanted to make. So as the electricity passes through the wire, it changes the shape of the atoms. The change in the shape is essentially the idea that the electron is going to push out. Like that, okay. And if I maintain the pressure, it stays out there. But if I reduce the pressure, it goes back, and then it can go forward again, then it can go back and go forward. So now you can see why it has to be an alternating current, to be able to create the change, the frequency change. I have to keep this thing moving, okay, to be able to maintain a signal, or to keep creating the compression. Creating the compression once, okay, well that's a signal. That's why you receive one signal. So I charge the system, it creates induction, and then the needle goes right back to zero. No more induction. I have to keep discharging the system so I can keep causing this to happen on the surface. I have to keep the surface oscillating. And that's why AC current will create that magnetic effect, but DC won't, unless I do it a completely different way. All right. So it's perfectly understandable. And so what's it really doing is it's just creating those compressions, and then it sends the compressions through the atmosphere, and they hit this wire. So let's say those compressions are coming now. They're going to hit the wire, some other wire. They're going to cause the same effect. They're going to hit the wire. They're going to compress the atoms in this direction, okay, and force the electrons to move this way and this way. So that's, the reciprocal effect. So you can use the thing you transmitted to recreate what it caused, the thing in the first place. So we know that changing the shape of the atoms causes the effect, and then the effect goes through space, hits a surface, and it essentially just does the exact opposite. The effect ends up duplicating the cause, and you get the flow of electricity. So that's pretty understandable as a diagram. But it's just understanding that this electron doesn't have to excrete anything. All it has to do is move, and it's going to reflect. So the energy in the external universe is what's bouncing off the wire. The wire isn't producing a force going out. What it's doing is pushing electrons out, and then the force is reflecting off of them. So the magnetic effect, or the inductive effect, isn't using the electricity. It's just a byproduct of changing the shape of the atoms. So the change in the shape is using the electricity, not the effect of pushing on the external world and causing a change in the frequency. All right, yeah, that's pretty good, I think. All right, so, oh yeah, I can't erase that color. I shouldn't have drawn in that color, because I can't erase it. All right, do I have anything here? Well, I can always try a little bit of coffee. Right? Coffee's good for a lot of stuff. Yeah, maybe it'll work. Right, yeah, coffee will work. Sure it will. Coffee does everything. Let's see. Oh yeah, it almost works. Yeah, see, it's almost working. Yeah, well, it's close enough, right? Yeah, you can barely see. It's a little purple, no big deal. Okay, so that's close enough. All right, so I really need both colors for magnetism, but I will try it without, just for the fun of it. All right, so it gets more complicated now when you talk about how, but we all know that magnets have this property. So I'll do a circle and a square to define north and south. And that, what you're basically doing is just taking this north-south connection and you just end up piling them on top of each other. And that's how you create a magnet. A magnet's made out of a bunch of little magnets, okay? And the little magnets are electrons and protons, as I just described. The smallest dipole is the neutron. So you could just say it's neutrons piled on top of each other. And the idea would be is you could sort of understand that as, in terms of looking at these things as they radiate their energy, they're obviously, if you looked at it, you're going to get a blend of the two forces. So we could just say the two forces are reflecting off of these two objects are different, right? All right, well, I can't do it. I should just do the red and purple thing. I mean, red and blue. And that, yes, they'll look purple from some locations, blue from some other locations. So instead of changing frequency, what's happening is the external world hits the electrons and protons, and it ends up being reflected or absorbed, okay, based on whether it hits an electron or it hits a proton. And so the image you're getting as a reflection is going to be a mixture of those two, and obviously they're all pointing in this direction, so you can understand that it's going to be all red coming up the top and all blue coming out of the bottom in a sense, but it can't be all right, because they can't be right up next to each other, so there's space between them. So you can understand that even though this is a block here and there's a little blue one, you can see the blue from this angle and you can see the blue from this angle, so it's not perfect. And so what you end up with is some idea where you can understand that. So it's not a frequency, but again, it's another pattern match. And so what you really have is two different kinds of bullseyes. You have the bullseye that starts black in the center, and you have the bullseye, okay, that's clear in the center. And all you're doing really is when magnets match, they're matching opposite patterns. That causes attraction. When the two patterns are the same, then they repel. And that's really, so only dipoles can see this dipole pattern. So this is a dipole pattern. Only other dipoles can see the dipole pattern or react to it. And so the material has to have all of its electrons and protons aligned, okay, to maximize this magnetic effect. And so if the little atoms, which are all magnets, are turned in different directions, well, then the bullseyes are broken and the pattern is gone, and the dipole can't see it, obviously, because it doesn't exist. All right, so that's the simple diagram of the fact that magnetism is just another change in the force. So this force is just representing vectors, okay, where this is the bullseye created by the red force is doing this, and the blue force is doing this stuff in between, and the red force is doing this part in here where you can see it. So it's just changing what you're seeing. And and again, the pattern, I'm drawing the pattern as if it has a shape, but again, it's line of sight. So, theoretically, I could take two neutrons and have them, a million miles apart, and they would still be sending straight line force between each other. So it's, technically they can see each other over, vast distances. Yeah, so that's adequate. That I should be able to erase, which is good. All right. So what else? All right. So you can understand that it's just about force and matter. That's the only two things there are. So the matter has this mass and that allows force to be consolidated or collected in its motion. So every time a piece of matter moves, it has to collect a bunch of force bits to do it, increasing the density of the force. So essentially, if I had a total density in the universe, you could understand the more matter there is, the less density there is in the force. So the matter consolidates the density, which means it had to take it from the density of the external world. So you could kind of argue that in the full universe, with all the galaxies and all the stuff, you could understand that there could be a real balance between how much the galaxies expand or contract. So the more they contract, the more force they consolidate. That means there's less force outside, which means there's less pressure, which makes them expand. So you can understand that the whole universe could just be in a cycle of expansion and contraction, where as soon as the gravity gets weaker, they expand, and as soon as it gets, as soon as they expand, which means it's putting the density back out. So as soon as it expands, there's a huge interest in collapsing again because you've just increased the density of the force in the free space. So you just have that balance. So every time a supernova happens, a bunch of force goes back to the field, as speed of light force, which increases the capacity of gravity being created somewhere else, pressure being created, and so it increases the gravity that other things are going to experience, the amount of force. And then that subtlety happens over some other one, expands, and it pushes that stuff back together again. So everything's just in an oscillatory condition of getting bigger and smaller, rather than any universe that needs to evolve. It just keeps doing this, over and over and over. I'm not saying that objects don't evolve in the universe. Maybe they over time get bigger and bigger, and then it all consolidates into one big ball, and then that ball explodes like a supernova. Maybe that's the reoccurring process that they call the Big Bang, is just the idea that the universe tends to always collapse eventually. Then it collects all the pressure is inside the matter, and there's no pressure on the outside, so it has to expand. So it gets to some point where the pressure can't be maintained, and then the object catastrophically explodes because it doesn't have the capacity to resist the desire of the pressure to go from high pressure to low pressure, and it does some kind of chain reaction, some kind of blah blah blah, that causes that catastrophic release. So we know that happens. We know that suns do explode. And the only reason why they explode is because there's some mechanism that's saying the electrons and protons can't stay stable. And that process ends up creating way too much pressure inside. And that high pressure, like dynamite, just, forces everything to fall apart. All right. So I don't hate any of that. Just think of what else I had to go over. I'm just saying this simple diagram works. It explains the universe, explains why electrons move, explains how you move them, explains why atoms stick together, why atoms don't like each other, generally speaking, and they only like each other when they're sharing electrons. So if they're not sharing an electron, they're not going to be anywhere near each other. They're going to want to stay independent. So they have to be in some kind of ionized condition where they have a little bit of desire to stick, in the right position. So if you have them rolling apart around each other, each one could have a spot, where that nucleus is showing a little. And it's saying, I can accept an electron here. So if you can get your electron on your atom to fall on just this location, we'll be stuck together. So they're, and that's what causes like elements to be able to stick to each other. But again, it requires the external pressure. for any of that to happen. I don't know what those notifications were for. Interesting. Let's see. Storage space is running out. Oh, well, I don't think you need to notify me of that. Thank you. Yeah. Fuck you. Anyway, so let's see what else. All right, it's mind-boggling. People don't get this. So, but that they don't get that this is a viable alternative, and they won't even concede that. Like somehow they're going to argue it's nonsense and it's rubbish and it's insane and it's, you know, outside the bounds of reasonable, when no, every piece of it is perfectly reasonable and it does actually work. So I mean, I have the simulation showing the charge. It's going to be a better simulation soon. Stop doing that, cunt. Anyway, what the hell is it could possibly be doing this for? There's nothing running that's using up space. I guess it just decided to do a bunch of notifications now instead of later. So, yes, screw you. I don't need this crap. Notifications. Jesus. Irritating. Anyway, useless. So that's the argument that's so profound to me, is that the people of a scientific mind can't realize that, yes, physics made lots of mistakes in the past, so let's get serious. Descartes was way off. Okay, I mean, Descartes' theory of ether was that everything has this swirling vortexes. So everything was vortexes, and that's why the moon was moving into the earth, is because their vortexes were swirling in opposite directions or some sort of horse shit. I mean, way off. Well, all the ether theories are way off, and I sort of explained this before, but you can understand that whatever you make your ether out of, it has to have a geometry. And so you're stuck, okay, with the fact that you can't have a straight line with a geometry, right? That a straight line that has the same distance. I mean, I can go this way or I could go this way, but if I do this diagonal thing, I'm way off. I got a line that's too long. So I can't move in any direction. And you can just understand by looking at it that there's no way. I mean, I'm going to run out of vectors, right? I'm going to have this way and this way, but what about all these other ways? I can't go any of those ways because there's no connection. You know, the other next block is too far away, so I can't reach it. You know, going diagonally across a square, you know, it's way far away. So I can't possibly have straight lines. So obviously this doesn't create a universe with an infinite amount of straight lines. You know what I mean? An infinite capacity to move in any direction. And we sort of know that, yeah, that's the real universe has that. I mean, I can make a straight line in any direction. I'm not stuck where it has to jump from here or here. No, I can have the choice of anywhere in between. So, I mean, ether really doesn't work. I mean, there's no geometry that's rational because the distances change. And if the distances change and the speed is the same, you can't have greater distances and the same speed, and you can't have the same vibrating pressure over different distances, so none of it makes any sense. But you can't have any straight lines. That's the real bottom line. I mean, you can only have straight lines that fit in that geometry, and there's no if you use chaotic geometry, that won't work either, because you're still stuck with a bunch of different distances. So it really doesn't work. It's the same. It's a simple argument. It doesn't convey energy the way we see energy conveyed, which is very vector-like and very straight-line vectors. So, fail. All right, so let's see. This guy says good work. Well, thank you, but it's all for naught. But this happens a lot in the past, right? People made assertions about even the existence of atoms, and everybody shit, no, fuck you, you're wrong. And, 40 years later, they acknowledge that, oh, yes, atoms were right. Yes, there's atoms, that kind of thing. So there's so many examples of that throughout this history of physics. And it's only the modern world where, we're back to God. We're back to a point where you cannot possibly argue that they have got anything wrong. And they're just going to keep telling you it has to be a wave, and it has to be entanglement, and it has to be interference, and it has to be this, and it has to be that. And they don't have any evidence to back any. Again, you can't argue there's no quarks, but they have nothing. Their evidence of quarks is the deflection of electrons off of a proton. Even the very idea that they could even, obviously they could never deflect a single electron on a single proton and collect the electron. So this doesn't have anything to do with some real experiment. This just has to do with their approximation, and their assumptions are, well, if I change the direction the electron's going, that means I hit a different particle. And no, that doesn't mean you hit a different particle. You just mean you hit a particle in a different state. So, which gets to the double slit. I mean, I could do that real quick. The simulation I'm going to have created is going to be pretty simple in the sense that all it's going to do is show that right? So the electrons are constantly moving in and out of the surface, all right? And they have a momentum, as I just pointed out. They're going very fast when they start moving out, and then they go very slow and then stop and then move the opposite direction. So they're going fast and slow, then slow, then fast. All right, so they're always fast close to the surface, and they're always slow far from the surface. So the simple argument is I just can make a plunger, that goes out and in with those rules. And the simple idea is the photons come through. The ones that go right straight through are fine. They're still photons. But the ones that go by the surface ends up combining their momentum this way with whatever the momentum of that rod is when they hit it. So if they hit the rod when it's moving fast, that way, then they'll get bent that way a lot. If they hit the rod when it's going slow, then they get bent a little bit. They hit the rod going the opposite way, obviously, they go this way. So it's a perfect scatter machine. So any bit that hits this rod is going to end up getting scattered. And it's going to be a perfect scatter pattern, perfectly even, in this dimension, right? It's not scattering them up and scattering them down. It's scattering them this way and that way. Just by combining the momentum. So the simple idea is the photon has an energy going this way. The electron already has a force going this way. And all you're saying is yes, the two vectors add up to this way. The electron moves this way, which means it compresses the force this way. All right, it's not really projecting a force. It's just causing one by changing its motion. It's moving into the field. It's reflecting. It's causing the compression in the right direction, okay? And the compression, okay, is the compression of bits is what you make the photon out of. Remember, it's the compression of the bits is what the frequency is made out of. So you're causing that compression to move in a direction, and the idea is the two surfaces are doing that, and you're going to take a bit from this surface, that's going to represent this, and then you're going to have a bit from this surface, which is going to be the next bit, and then you're going to have another bit from this surface, which will be the next bit, and you're just going to rebuild photons. And that's going to be the simple argument. That's all the double slit does. So the fringe light, all the fringe light is created by the surfaces. The bright center is caused by this opening, obviously. Most of the light just goes straight through. So if you do a single slit with a very wide opening, 97% of the light will just go straight to that center. And you start closing the opening, then you start changing the percentage, and now you get more light in the fringes than you get in the center. Because none of the photons can get through, theoretically. You make it narrow enough, then all the light will be fringe light, and you won't have hardly any light in the center. I mean, no more than you have on the fringes. So it'll become duller and duller. The middle will become flatter and flatter in its intensity the smaller the slit opening is, which is perfectly revealed in the pattern. So all of it makes sense. And the simple truth is I just keep throwing pieces, okay, essentially in these directions, and the simple truth is that there's a 50-50 chance they're going in phase versus going out of phase. And so obviously that creates the pattern, your geometry, the vector lines. You're recreating the frequency, and that's all you're doing. It's just recreating the photon. And you're doing it out of pieces from one surface and pieces from the other surface. So if you only have one surface, you can't create a fringe pattern because you don't have a second surface. Simple enough truth. But it's a perfectly viable explanation. No interference, no entanglement, no superposition, no Heisenberg bullshit. None of that crap has to be believed. A simple mechanical explanation works. And it works really well. Alright, so let's see what else. Yeah. So it's all on the website, frankly, the subjects. I mean, the one that's taught, and I'm just saying the one that's just gotten huge in my brain is this gravity one, because it's just so obvious that physics is moronic in its description of why the Earth is hot. When it's so obvious that gravity creates this insane pressure. So we know all of the pressure inside the Earth. You'd start digging down and the pressure gets intense, right? You go a few miles down and it's this gigantic amount of pressure. So if you don't have something to contain the rocks, they'll just crush you under the intense pressure. Even the atmosphere becomes so heavy, you'll suffocate and you'll be crushed, by the atmosphere alone. So insane amount of, the weight of the atmosphere is enough to crush you. Even if you could make yourself a tunnel, to go down, and you could hold the rock from crushing you, the air itself will crush you. But anyway, so insane pressure. And how can they not say, okay, gravity creates the pressure? Obviously, in what circumstance do we not understand that when you're increasing something's pressure, you're going to make it hot? I mean, there's no circumstance where pressure isn't associated with heat. And, and the transfer of energy and the effect of heat loss. So it's just, it makes so much sense. You're just saying, how could they possibly have any other theory? I mean, obviously gravity creates the heat, and the heat represents stored energy. Heat is energy. Okay, it's not very useful in a lot of cases, but in some cases we get something out of it. You can make a steam engine with it. You can, you can use heat, but yes, it's not terribly efficient. It's better not to have motion in all directions. It's better to have motion in one direction for ease of use. For our case, a stream is really easy to use, but it's energy all in one direction. But explosions are also, look, we use them in a car engine, So explosions work. Energy released in all directions does work, as long as you can build a device that can catch it and control it. But yeah, that's heat. It's all heat. Motion of mass, okay, can just be understood as you are storing energy. So any place there's heat, there's stored energy. There's a condensation, a higher density of force, a higher pressure. So heat is pressure, heat is weight, momentum is weight, momentum is heat. Heat is converted directly, motion is converted directly into heat easily. I mean, Joule proved that. Joule wasn't too smart in the sense that he didn't understand what gravity was. he thought it didn't matter how fast you move something in gravity. It was always the same amount of work, and it's not the same amount of work. You move it slowly, it's a lot of work. You move it quickly, it's very little work. So the fact that he didn't understand that ruined his analysis of his own experiments. All right, so I'll take a little break and see if somebody can say something challenging or inquisitive. Are you curious about anything? Have I left anything out that you still find mysterious about the function of the universe? Is there something about the Sisyphus boulder idea that seems implausible? That there's force, it has all the motion, and then there's matter, it just has mass. And so it's just matter is a force carrier, and by force carrier you're really saying force collector. So matter collects and consolidates force. So wherever there's matter, there's a higher density of force. Yeah, it's pretty good. Yeah. So anyway, but yeah, so that was it's how many hours you should need to explain the universe, in terms of all these mechanical functions. And I guess the answer is, hour and a half. yeah, whatever. You should be able to do it. But it's putting it all together. Yeah, you probably need the 6 or 7 hours if you add up all the experiments that you have to cite and explain how they've misinterpreted them or perverted them. So again, I could talk forever almost on the double slit and how they've completely lied about what takes place. I mean, they, to call the electron experiment a double slit experiment is ridiculous because there's no double slit. And then to call Stern-Gerlach experiment measuring the magnetic moment of electrons or the spin of electrons is ridiculous because the experiment is with atoms. There's no electrons and protons in the experiment. Technically the electrons and protons are in the atoms, but it's the atoms that are doing the motion. You're not watching electrons, you're watching atoms. So, I mean, there's just so many distortions and perversions. I guess I should see how many people are here, and then I'll know whether there's any reason to hang around and such. Because if you're not going to participate, then I probably shouldn't either. Yeah. Where the hell is it? Oh, there it is. 7. Yeah, 7's pretty low. So that's unfortunate. Yeah, I don't know why. I know Google, does try to silence me on YouTube. Because you can just see it with the numbers. You'll do a short for a week and you get 400 views, and the next week you get 200. I mean, it just seems kind of obvious that they're not giving it the same exposure. Hey, the chat's working. Isn't that interesting? Oh, okay, that's it's working in my account page, which it wasn't doing before. It usually doesn't work. I don't know why it's working today. I wonder if I can pop it out. I can have 2 pop-out chats, so I won't bother trying. Let's see if they're pop out. Okay, I'll have to try that. That'll save me some trouble. Maybe it only works when I open it in the other account. So maybe I just never noticed. Hard to say. Anyway, not your problem. That's an internal problem. Me and YouTube don't get along. Alright. So I guess it's like a 2-minute warning or something. So if you don't have anything to add, then I will Move on. Should have the gravity simulation pretty soon. I have a, there was a version made, but it was synthesizing the internal exchanges of energy, and so I'd rather that there was some mechanism that duplicated it more accurately rather than just synthesize it. So we're going to try to do it a little more detailed, a little more honest, I guess the word would be. A little more complete. Yeah, that's the word to use. A more complete simulation. I mean, it was perfectly accurate, and it did create exactly what you get, which is, you can create orbits, and you can make things crash, you can do all that stuff, so it worked fine. The one problem is, too, you can't duplicate the inverse square law in 2 dimensions. So that's another, it's a defect, but it's not catastrophic. You just change the velocity of the orbit, to compensate for the fact that you don't have an inverse relationship. Well, you don't have the square relationship. Anyway, the idea works simple enough that energy goes into the earth, heats it, gets delayed by the process of creating the heat, gets consolidated and made more dense by getting collected, making the heat. And so less at this exact moment, more force hits me from above than can get to me from below. Because the force that would have gotten to me from below is busy heating the earth. So you can understand that it's busy working, doing work, and that's why it can't do work on me. So I have to fall into that differential. There's no choice. And the only way I could fix it is I could wait until the stuff that's trying to get to me finally does get to me. But how can I wait? I can't. I need a force to keep me from falling. And there's no, I'd have to artificially create that. So I'm just saying that's the easy way to understand it, is that it's at equilibrium a second from now, but it's not at equilibrium now. It really is so simple, and it's just like, they had the kernel of this idea, 400 years ago. I mean, Fadier, a guy not much respected by history, Fadio, suggested that yes, you could just make gravity out of a particulate force and just concede that the Earth absorbs some percentage of the force, so you always have less hitting you from any material object between you and a force. The material object will absorb some of the force, and therefore you can't get hit by it, so you have to fall into that differential. And it's just so simple and obvious, and it makes so much sense that you wouldn't discount it lightly. And the truth is, as the history demonstrates, it was rejected lightly. I mean, they didn't give it any. They didn't try to make it work. They just tried to not make it work. They just tried to find flaws rather than to recognize it has an obvious simplicity, and the simplicity is so dramatically consistent with what we see happening. It just works so well. And to discount a theory that works so well lightly, with light inspection, it just demonstrates that this physics really is just a religion. It's just about what the leaders or the controllers or the authorities declare the truth to be, and all the sheeples and the followers and the people who don't know enough to say you can't do that, or you stop lying, the ones who don't know enough to say stop lying, fall for it. But there's no excuse for all these physics students to become physics tyrants. The fact that none of them seem at all curious and at all what's the word? Not suspect, but what's the word you use for? Jeez, I hate this vocabulary thing with age. Losing words is just so annoying. Skepticism. Why do they lose all skepticism? And they just become believers. It's just, I can't count for it. I just can't account for how smart people become unreasonable people. Because one of the first things you learn as a smart person is your fallibility. And so you always have to be open to, you got it wrong, you fucked up. So a funny thing I did do, I did ask AI to tell me about kinetic energy. And I think I asked it I didn't ask it the gravity question, but the answer was so funny. I should have it here somewhere. At least the link to it. Well, I can load it again. But anyway, it basically said that, it said things that were just really stupid. Like, so I made a video once where I said, twice the height, twice the velocity in gravity. So I was just totally wrong. And it was just so funny that the AI made the same mistake. So it was describing Galileo and gravity, and it said, twice the height is twice the velocity. And you're just saying, wow, it really shouldn't make that mistake, right? I mean, that's just such a, it's just wrong. And, it made a couple of, just glaring errors like that. And it's just kind of funny that it really can't defend its assertions, because when it tries to, it has to say something really stupid. And so anyway, maybe I'll put that in another video, because I just wanted to read the whole thing, because it was just so full of errors. And they were just such simple errors. I mean, so obvious errors. So it just shows that the physics is convoluted. They really can't explain how you can conserve both kinetic energy and momentum, because you can't. And only one of these theories can be right. Only one of them can be conserved in all cases. And that's the truth of it. And so you have to believe in momentum, or you have to believe in kinetic energy, but you can't believe in both. It's a violation of the basic rule that the universe can't just poof energy in and out of existence. Because if it could, then we could. And that's the simple truth. And we can't. So it doesn't. Yeah. If we can't do it, the universe can't do it. Simple enough statement. Alright, well, I guess I have to concede there just isn't any chat energy. So I will move on and do more productive things than talk to myself. Yeah, so till the next time, and such and so forth and whatnot. Where's the right browser? Here it is. Okay. So till the next time, and such and so forth and whatnot.